Welcome to the lesson on polynomial and rational inequalities. We are going to look at these inequalities with mostly a focus on using graphs to help us to solve them. But I'll also include a little bit more information about how to look at it analytically, but mostly the focus will be on the graphs. Okay. So what are we looking at first? We're going to look at polynomial inequalities first. So if we let f of x be a polynomial, we've been talking about polynomials quite a bit lately, so you should be pretty familiar with those. And then a polynomial inequality is an inequality that can be written in the form f of x, remember f of x is a polynomial, so some polynomial less than 0. Or you could say f of x less than or equal to 0. Or you could say f of x greater than 0. Or finally, f of x greater than or equal to 0. So that's it. It's probably exactly what you were thinking it would be. Now, when we go to solve these, as long as you have 0 on one side, it makes it a lot easier. Because then you can look at your polynomial and determine, what values, for less than 0, what values come out negative. What values of x, when you plug in, give you a negative result. If you're looking at greater than 0, you're looking at, what values, when you plug in x, give you a positive result. And for these, you're going to be looking at intervals. And this book definitely uses interval notation for a lot of this. All right, so how are we going to solve? How to solve graphically. All right. Rewrite the equation or inequality, which we're dealing with inequalities, but if you have an equation, it's the same idea. To have 0 on one side. If needed. If it already has 0 on one side, then you don't need to worry about that step. But if it doesn't, do that. Okay. Graph the side that is not 0. So you could say, well, that side, we'll say it's f of x equals whatever, and it would be like a function that you're graphing. So treat that side, instead of treating it as an expression, treat it like it's a function and graph it. And then use the graph to determine solutions. If you have your x-axis, the points on the x-axis, those are your zeros. So those are the values that'll solve f of x equal to 0. The space under the x-axis, that's for f of x less than 0. Space above the x-axis, that's for f of x greater than 0. So you're going to be looking at your graph. You're going to be looking at, well, if I want it to equal 0, I'm going to look at where does it cross the x-axis. If I want it to be less than 0, where is it below the x-axis? If I want it to be greater than 0, where is it above the x-axis? And then just keep in mind, too, like when you're using your interval notation, If it's less than or greater than, you're going to use parentheses for the intervals. If it's less than, equal to, or greater than equal to, you're going to use the brackets for the interval notation. So that's something to remember too, because brackets include the values where it equals. All right, let's do an example. Okay, let's say you have the function f of x equals -2 times x plus 1 times x minus 3. Okay, so what does this graph look like? What does this graph look like roughly? I'm not going to be super exact doing this. All right, so you could set if you set f of x equal to 0, you can find the zeros. So the x plus 1, it's already factored for us, that helps. So x equals -1 is one of the zeros. And then x minus 3, so x equals 3 is another 0. And those have multiplicity 1. We know that the graph is just going to go right through the axis there at those two values. Our leading term, if we multiplied out those factors, is -2x squared. So we know the end behavior is going to be like that. And in fact, I'm not really concerned right now about all the details of this graph, so I'm just going to sketch it real quickly. Because what I am concerned about is figuring out where f of x equals 0, of course, where f of x is greater than 0, and where f of x is less than or equal to 0. Okay, so the example that I pulled out of a book, that's what they want me to actually find for this. So it equals 0 at two values, just two specific values, not an interval. So we can use the little set braces to list the -1 and the 3. We use little set braces when we're just listing single numbers. Now for f of x greater than 0, for this one, we're looking at where is this graph above the x-axis. So for that, it's above the x-axis between -1 and 3. Now they just said greater than and not greater than or equal to, so we're going to use parentheses and not include the actual -1 and 3 values. But we want to include everything in between. So this interval notation says, I can get as close as I want to -1 and as close as I want to 3 without actually including those two numbers. All right, and then less than or equal to 0, that's looking at which parts of the graph are below the x-axis. And then it's equals to also, so we're actually going to include those points where it touches, or the zeros. So from -infinity to -1, including -1, union, including 3 to infinity. And there you go. So we ended up using the brackets there because we wanted to include that -1 and that 3. Infinity always has parentheses because infinity is just a concept. You can never actually get to it, touch it. It's a directional concept. Now, if you're doing this analytically, you would be able to take the zeros of the function and say, well, the zeros divide up the x-axis into 3 intervals. And you know that at -1 and 3 it's equal, but you're interested in seeing what's happening inside those intervals. So you can do a little chart, and you can pick some values in each of the intervals and plug them into your function. Like, let's say for the interval from -1 to -2, or -infinity to -1, sorry, I picked the value -2. If I plug that into my f of x, into my function up there, I don't even really need to know the value, I just need to know the sign. But if I plug it in, I'll have negative 2 times negative 1 times negative 5. So that would end up giving me a negative result. If I plugged in 0, I'd have negative 2 times 1 times negative 3. That would end up giving me a positive result. And if I plugged in 4, I'd have negative 2 times 5 times 1. So that would be a negative result. And I would want the interval, for the greater than 0, I'd want the interval that gave me the positive result. And for less than 0, I want the intervals that give me the negative results. So even if I don't have the graph, I can do it analytically by finding the zeros, because that's for this kind of graph, for this quadratic, the zeros are going to be where it changes from either being below to above or from above to below. And that's what I'm interested in. I'm interested in seeing what's happening there, if there is a change. If there's no zero, if there's no real zeros, if it's all, the non-real complex, then the graph is floating. So it's either going to be entirely above or entirely below the x-axis. If there's only one real zero with multiplicity 2, then it's touching the x-axis in one spot, and then your graph is equal, like above or below the x-axis plus touching it, equal to 0 at the vertex. All right, anyways, let's move on to another example. Okay, the next one is f of x equals, f of x equals negative x, parentheses, x minus 1 squared. Okay, so it's already in factored form. That was so sweet of them. So I can see here that my zeros are going to be 0 because of the x, negative x there, x equals 0, and 1 with multiplicity 2, because x minus 1, x minus 1. All right, and then if I multiplied it out, my leading term would be a negative x cubed. So then I know my in behavior would be something like this. All right, let me actually just do a quick sketch of the graph. Okay, I can plot my zeros, so 0 and 1. And then I know how it's roughly supposed to look, but I go ahead and just pick some values of x to get a better idea of the shape. So I plugged in negative 1 and got 4. I found out by cheating a little with Desmos that this comes down at 1/3 comma negative 0.148, and that's where it kind of, when it comes down, it just dips down slightly, comes up, and then remember this was multiplicity of 2, so it bounces right there. And when I plugged in 2, I got negative 2. And I plugged in a few more values, but honestly, this is enough to get a good idea of the shape. All right, and so for this one, we're interested in where does f of x equal 0? Where is f of x less than 0? Where is f of x greater than or equal to 0? And where is f of x less than or equal to 0? Well, equals to 0 is pretty quick. It's the two zeros. And since we're just listing two values, we can use the little set braces and say 0 and 1. That's the two zeros. All right. Less than 0, remember that's where it's below the x-axis. So like when you do your xy table, that's where the y values are all come out negative. So for that, it's below the x-axis from 0 to 1, but not including 0 and 1, because we're just doing less than. And then it's also below the x-axis after 1 to infinity. We have to leave 1 out because 1 is a 0 of the function, and that's where it equals 0. And our question there is only asking for less than. Greater than or equal to would be all the stuff above the x-axis and where it equals the x-axis, where it equals 0. So greater than or equal to 0, you're looking at negative infinity to 0. Remember, this is the x values I'm putting in these intervals. So include 0 because it actually equals 0 there. And then the only other place where it equals 0 is at 1. So we'll say union, and then we'll do a little set braces just to list the number 1. All right, and then less than or equal to 0. That's going to be back to what we were looking at earlier with less than 0, but now equals to will include the 1. So equals to is going to be not just what we have in blue here, but also where it touches where it is on the x-axis, where it's the zeros. So less than or equal to 0 is going to be bracket 0 to infinity. Because from 0, it's on the x-axis, then over to 1, it's below the x-axis. At 1, it's on the x-axis, and then down to the right, it's below the x-axis again. So it looks kind of like the less than 0, except now 1's included, so we don't need that little parentheses union business. We can just say bracket 0 to infinity. All right, and again, greater than 0, all the y values are positive. Less than 0, all the y values are negative. You could always set up these little intervals and do a chart, and you could figure out, from negative infinity to 0, from 0 to 1, from 1 to infinity. If you do a little chart and like pick values inside those intervals and plug them in, you would quickly see your signs. And your signs would tell you what's happening there, what that behavior is. Positive signs above the x-axis, negative signs below the x-axis. All right. Let's do one more polynomial inequality. Let's do 9x to the 4th minus 10x cubed plus 4x squared is less than or equal to 20x cubed minus 14x minus 3. All right, if I want to do this, I really need 0 on one side to make my life easier. So I'm going to go ahead and move everything over there to the left. So 9x to the 4th stays the same. But when I subtract 20x cubed, I'll have minus 30x cubed. Plus 4x squared stays the same. I'll be adding 14x, adding 3. That way, I have 0 on one side. Life's a whole lot easier this way. All right. So I see my leading term is 9x to the 4th. So I know that my end behavior is going to look like this. But I need to find my zeros of this function. Without spending too much time sitting there and listing all the possible zeros, etc., etc., I'm just going to say I already know that 1 and 3 work. You might find that by trial and error. I just am lucky. Often I like to start with 1 and it worked. And then of course I have the teacher's edition, so I can already see how this works out. But anyways, all right, so I can do some synthetic division starting with 1. And it does work out, so I know that 1 is a 0 of the function. Yeah, this 0 remainder tells me, oh, I've got one of the zeros now. And then you would have to do a little trial and error with some of your possible zeros. I know 3 works, so I'm going to go ahead and jump for time's sake and use it. I don't think you want me to spend the whole time sitting here guessing and checking on zeros. So unfortunately, there's not a quick way to do that if you don't get, luck out on your choices. All right, so when you do the 3, again, you get remainder 0, so that tells you it's another 0 of this function. And that leaves me with 9x squared plus 6x plus 1, which factors. It's a perfect square trinomial. So I know my zeros are 1, 3, and then negative 1/3. But negative 1/3 has a multiplicity of 2. So that's some good information for getting the graph of this. If nothing else, you don't have to graph it. You can always set up you can do analytically. You can set up your intervals from like negative infinity to 1, 1 to 3, or negative infinity to negative 1/3, excuse me, negative 1/3 to 1, and then 1 to 3, and then 3 to infinity. And you can put in some test values and see where the graph's above or below the x-axis. In this case, we want it below because we're doing less than or equal to 0. We want it equals and less and below. All right, but I'm going to go ahead and graph it. So real quick, sketch the graph. One of my zeros was at negative 1/3. I know the graph is that had a multiplicity of 2, so the graph's going to bounce there. One of my zeros was 1, and one of my zeros was 3. Sorry about that extra stray mark there. Then if you start plugging in some numbers, like if you plug in negative 1, you get 32. Because you get 9 plus 30, so 39, plus 4, 43, minus 14, so 29, plus 3 is 32. So I know that this thing's going to be shooting way up right there, because 32 is going to be really high up there. And I know it's going to bounce there. So maybe I should draw it more like this, because I had that multiplicity too. So it's going to do that lovely bouncing. And if you plug in 0, you get 3. So 1, 2, 3. So it comes down, bounces, comes up, and actually it keeps going up. If you plug in 1/2, I did it on Desmos, and I know that that comes out to 7.813. So it goes up there, and then it comes back down. Now 0 of 1 only had multiplicity of 1, so we know it's going to go through that. And then this actually down at 2.333, negative 56.889. So it goes way down before it comes back up and goes through that other 0 of 3. But anyways, ultimately we're trying to figure out where is this graph less than or equal to 0. So we're trying to figure out where it touches the x-axis and where it's below the x-axis. The equals to is where it touches, the less than is where it's below. So it touches at negative 1/3. That's kind of lonesome because it's right there. Remember, that's got that multiplicity of 2, that 0 does. So the graph comes down, bounces, like touches at negative 1/3 and then shoots right back up. It does not dip below the x-axis right there. Then it picks up again at 1, including 1, and then it's below the x-axis up through 3. For every other part of the graph, it's above the x-axis. So every other part of the graph would be greater than 0. So there you go. All right. I've already got a video on this, but since it's in the lesson, I decided to go ahead and do a couple of examples again anyways, because this lesson also likes to throw in rational inequalities. So I have that video that'll give you a lot more details, but I'm just going to go ahead and go through some couple of quick examples. First one being x plus 3 over x minus 1 greater than or equal to 0. So just like the polynomial inequalities, greater than 0 means above the x-axis, less than 0 means below the x-axis. And then equals means the actual zeros, like where does it cross the x-axis or touch the x-axis. So that concept is still the same. But we just have to be careful graphing it and make sure we graph the rational function correctly. So like if we were graphing f of x equals x plus 3 over x minus 1, we would look at the vertical asymptote, which is what would make the bottom 0, so x equals 1. And then we look at the horizontal asymptote in this case, because the degree on top is 1, the degree on the bottom is 1, so it's y equals the ratio of the leading coefficients. If the leading terms have the same degree, then you just do a ratio of the leading coefficients. So y equals 1 would be your horizontal asymptote. And remember, the graph cannot touch the vertical asymptote, but it can possibly touch the horizontal asymptote. It may not, but it is possible. All right, so then you go to graph it. You know for sure that at y equals 1, you have that horizontal asymptote. At x equals 1, you have that vertical asymptote. What else do you know? Well, as far as intercepts are concerned, if you plug in 0 for x, you get negative 3. So the y-intercept is at 0, negative 3. And if you plug in 0 for y, so what basically would make the top 0, that would also be a negative 3, but this time it's on your x-axis. So your x-intercept's at negative 3, 0. And you can fill in a couple of points in between if you'd like. Like if you do negative 1, plug that in, you get 2 over negative 2, which is negative 1. Depending on how perfect you want your curve, you could do more, but it's going to be this nice little curve here. Sorry, that's so sloppy, but it goes off to the left. It gets closer and closer to the horizontal asymptote, but it doesn't actually cross it. And then off to the right, it goes down. It'll get closer and closer to the vertical asymptote, but not actually touch it. But that's not all, folks, because this graph also has a piece over there in the diagonal quadrant from the asymptotes. So like if you plugged in some of those values, you would get some other interesting results. Like let's say you plugged in 1.5, 2, and 3. If you plug in 1.5, you get 4.5 over a half. So 9 halves times 2. So you end up with 9. So that's going to be way up here. And if you plug in 2, you get 5 over 1, which is 5. If you plug in 3, you get 6 over 2, which is 3. So 3 comma 3, 2 comma 5, that's up here. So it's like that. So it's this curve going like that. Going to the left, it gets closer and closer to your vertical asymptote. Going up, then going to the right, it comes down and gets closer and closer to your horizontal asymptote. It doesn't actually touch it. But what do we want to know? We want to know where it's greater than or equal to 0. So greater than equals to is where it touches the x-axis. So that's at this 0 right here. That's at -3. Greater than is where it's above the x-axis. It's above the x-axis for this piece shooting off to the left. And it's also above the x-axis for this entire piece. So from -3, or I'm sorry, from negative infinity to -3, including -3, since we're doing an equals to business, union, and then we have a vertical asymptote at 1. So the graph gets close to it but doesn't touch it. So we're going to use a parentheses 1, and then the graph shoots off to the right to infinity. So for greater than or equal to 0, you've got negative infinity to -3 with a bracket for the equals to part, union parentheses 1 to infinity for that nice curved part in the upper right quadrant there. Lovely, isn't it? All right, how about we do one more of these rational inequalities, because they are so much fun. Okay, so let's do 3 over x plus 4 is greater than or equal to 1 over x minus 2. Small challenge to begin with because I don't have 0 on one side. So I'm going to go ahead and subtract the 1 over x minus 2 so I can get it on the same side as the 3 over x plus 4. And I got my 0 that I need. Yay! But in order to effectively work with this, I really need these fractions to be combined. I need to go ahead and do that subtraction. So I need a common denominator. These denominators are already factored. You can't really factor them further. So I can go ahead and have my common denominator be x plus 4 times x minus 2. Just put the two factors together. But in order to do that, I have to take that first fraction and multiply the 3 with x minus 2. I have to take the second fraction and multiply the minus 1 with x plus 4. That's part of the whole process of getting common denominators with the fractions. And I kind of skipped a step and went straight to just writing them all as one big fraction. Let's clean it up a little. Distribute the 3 up in the numerator. Distribute the -1 in the numerator. Combine like terms. If you want, you could try factoring. I can see already this isn't going to help me much, but I'll go ahead and factor the numerator. You like to do that to see if it'll reduce any, to see if it's a graph with a hole or something. But this does not reduce. This is not going to be a graph with a hole in it. So that's where I'm at. It is still a rational inequality. So I think I'm going to go ahead and go to a blank slide and transfer this over there. I'm going to say 2x minus 10 over x plus 4 times x minus 2 is greater than or equal to 0. I'm going to graph that real quick. Vertical asymptotes, there's going to be 2 of them. X plus 4 equals 0, so x equals -4. X minus 2 equals 0, so x equals 2. So just set those that denominator equal to 0. Horizontal asymptotes. Well, if I multiplied out the bottom, I could look at my leading terms and see that the degree on top is 1 and the degree on the bottom is 2. So if the degree on top is smaller than the degree on the bottom, then automatically my horizontal asymptote is just y equals 0. So every time it's just y equals 0. That happens. Degree on top smaller than the degree on the bottom. All right, xy table. If I plug in 0 for x, I get what, 5/4? Same thing as 1 1/4. If I plug in 0 for y, I get 5. So that gives me some values to kind of start with. Zero comma 1 1/4 is about right there. 5 comma 0 is right there. I have vertical asymptotes, so x equals -4 is here. X equals 2 is here. Y equals 0 is on the x-axis, so you could always do it maybe in a different color or something if you want it to show up better, but at least you know where it is. All right, then fill in some values. Start plugging in some numbers. Like I plugged in -2, and when I did that, I got 1 3/4, because I got -14 over 2 times -4, so 14 over 8, which was 1 3/4. So -2 comma 1 3/4. I plugged in 1. I got 1 3/5. This ends up being a shape kind of like this, where actually the lowest point is in here at -0.196. Plug that in, you get 1.244. It's so hard to get it just right, but I don't have the grid drawn out exactly. Okay, and then there's 2 other pieces to it. If you go ahead and plug in some other numbers, like let's say you plug in 3. Continue my xy table like this. So you plug in 3, you get like -4/7, because you get -4 up top, and then you get 7 times 1 on the bottom. So 3 comma -4/7, so roughly in there. So this is going to end up being a nice little curve that kind of goes like this. So this actually goes through the horizontal asymptote, but it hugs it. As it goes to the right, it hugs that horizontal asymptote still, even though it went through it. And then if you plug in, you can plug in more values if you want more precise curves. I plugged in a -5, and I got -2 6/7. Oops, 7ths, not thirds. Because I got -20 up top, and then I had -1 times -7, so +7 on the bottom. So that's how I got to -2 6/7. So -5, -2 6/7 is here. I plugged in -7 just to get an idea, and I got -24 over 27 here. So it ends up being a nice another nice little curve that goes like that. This one actually does not cross the horizontal asymptote, because the only x-intercept we got when we plugged in 0 for y, we only got x equals 5 for our x-intercepts. So that curve over there on the left doesn't actually touch the x-axis. It just gets closer and closer to it. Whereas the curve way over there on the right goes through at 5 and then hugs the horizontal asymptote. All right, and that's enough, because ultimately we're trying to figure out where this thing is greater than or equal to 0. We're trying to figure out where is it above the x-axis. Well, it's definitely above the x-axis here for this piece. So that piece between the vertical asymptotes from -4 to 2. But it's not touching -4 and 2, so we use parentheses. And then it's above the x-axis and touching the x-axis from that x-intercept onto the right. So that x-intercept being 5, so we'll do a bracket, 5, because that's the equals to infinity, because it shoots off to the right. Everything else is below the x-axis. And that's it. So that is your solution to that inequality. If you were to, if you were doing this analytically and trying to set up your chart, you would consider your vertical asymptotes and you would consider your x-intercepts, because those are the values where the graph may shift from being below to above or above to below. And then you could put in test values and see, do my test values give me a positive number for greater than 0, or do they give me a negative number for less than 0? And go from there. All right. Well, I think that pretty much takes care of this lesson on polynomial and rational inequalities. Thank you for joining me. So that wraps that up, and we have a lot ahead of us in this course, so I look forward to chatting again soon.